let's go over the ideas once again of the skydiver. Make sure we understand them. In the x direction, horizontally, there are no forces. This, of course, is without air resistance. There are no forces acting horizontally. Gravity acts only vertically. So if there's no forces, and the skydiver already had a horizontal velocity, the velocity of the plane, then there's going to be no acceleration. So acceleration for the skydiver horizontally is 0. The velocity is going to be whatever it was when he left the plane. It's going to stay the same because there's no acceleration. So how will distance change? The distance will increase at a constant rate. But what about in the y direction? In the y direction, there is a net force. In the y direction, vertically, there is gravity. So if we're ignoring air resistance, that's the only force, that is the net force, there will be acceleration. And that acceleration is going to be constant. Well, a constant acceleration will make the velocity constantly increase. So there's our graph of velocity. Incidentally, the slope of that line is going to be equal to the acceleration. The slope of that line will be 9.8. And how will distance increase? Well, at first, when the skydiver first jumps out of the plane, they're going relatively slow. So they're not going to cover a great amount of distance. Later, they're going very fast, so they're going to cover large amounts of distance for the same time intervals. So that graph is going to look like that. By the way, the slope of this line at any point is equal to the velocity at that same point right there. Okay. Okay, so what is this going to look like if we do include air resistance? We really need to include a free body diagram to start with. So if we draw our skydiver and consider the forces that are acting on them, we have the force of gravity. But with air resistance, it's sort of like friction. The air is pushing up on the skydiver, so we know it's an upward force. But it's a force, unlike most frictional forces, in that it changes with speed. You can think of it this way. If you're driving down the road in your car and you put your hand out of the window, at a slow speed, the air doesn't push on your hand very much. But if you're going down the highway at a high speed and you put your hand out of the window, it's going to push a lot. So when the skydiver initially jumps out of the plane, they don't have any velocity. Their initial y velocity is 0. So there's not going to be any air pushing up on them. So technically, right at that moment, they're in free fall. But as they start to gain speed, this force, this drag force, is going to get larger and larger. So it's going to keep growing and growing and growing. So how fast are they going to go? What's their maximum speed that a skydiver can fall at? Well, you can see that eventually what's going to happen is that the drag force is going to get so large that it becomes equal to the force of gravity. And at that point, the acceleration becomes 0. There's a name for this. It's called terminal velocity. Let's look at this as a net force equation. We have F net equals ma. Let's call down to be positive. So we have the weight minus F drag. Now, it turns out that for a skydiver, the drag force is equal to kv squared. This is turbulent flow, where k is some constant and v is how fast you're going. So can we find the terminal velocity? Sure. At terminal velocity, there's no more acceleration. So this becomes 0. And if we add force drag to the other side, we say F drag equals Fg. And so what's the terminal velocity? Kv squared equals mg. And what's v? I'm going to put a little t there for terminal, because that's my terminal velocity. Divide by k, square root of both sides. And I now have a formula for the terminal velocity of a skydiver. Okay, so what are these graphs going to look like if we do this with air resistance? This is definitely a different situation. When the skydiver first jumps out of the plane, there's, in the y direction only, there's no air resistance yet because they haven't started to fall. So it's sort of like they're in free fall for that initial moment of time. So there's their acceleration. Let's say it's 9.8 right there. And then as they start to fall, the velocity increases, so the drag force increases and their acceleration decreases. How it's going to decrease depends on what type of drag force it is. Maybe it's laminar flow, where it's equal to kV, or maybe it's turbulent flow, where it's kV squared. But for now, we're just going to say that it decreases. It goes down in some way. It doesn't go below 0, though. It's going to drop down there like that. So what's the velocity going to do? Well, when they first jump out of the plane, there's not much air resistance as they start to speed up because they haven't started to travel very fast. So their rate of change of velocity is going to be very high. So the slope of the line is going to be steep. But as they travel faster and faster and faster, the acceleration starts to decrease because the drag force is increasing. So the slope of this line is going to decrease. And it's going to become like that. And then eventually, this becomes horizontal. Let's see if this makes sense. Steep line, the slope of this line is the acceleration. As the slope decreases, so does the acceleration. Eventually, we get to this point right here. And if we trace that back, that is my terminal velocity, radical mg over k. Okay, what's that going to look like on a distance versus time graph? Well, with no air resistance, it just goes on forever and ever. It just keeps going faster and faster. This line gets steeper and steeper. It's asymptotic. But with air resistance, it's not going to continue to get steeper and steeper forever. Eventually, it's going to get to the point where the slope doesn't change, and this line becomes straight. The slope of that line right there is equal to the terminal velocity of this right here.